Okay, we're just looking at the equations that we use in a variety of applications. We're going to look at several applications today and talk about the differential equations that we write for those applications. Then in the next chapter, we start learning how to solve some of the differential equations. First application, population dynamics. Now, as I said before, last time we looked at the my double prime equals negative ky, which is the equation that you get for a linear restoring force, gives you simple harmonic motion. That's a second order equation. We don't really learn to solve second order equations until a later chapter. And it turns out that except for some of the details, those equations are fairly simple to solve, a little more difficult to necessarily interpret in some cases. And sometimes they get kind of hairy. Okay, well, anyhow, start with population dynamics. Now, this is a simple first order equation, just a y prime. And the equation, well, okay, the idea is that population increases at a rate proportional to the population. That's your assumption. Basically, the more critters you got, the more critters they're going to produce. And then those critters are going to produce new critters. So you're going to get more and more critters, and the more keep compounding. It's just the same idea as compound interest. For compound interest, your investment increases in value proportional to how much you've got. The interest you get depends on how much you've got. And then when you compound that, you're compounding your interest on a greater value, okay? Okay, so anyhow, your population increases at a rate proportional to population, which means rate at which something increases, the rate at which y increases is its derivative. And that's going to be some proportionality constant times your population. Okay, well, it's really easy to solve this equation, but we'll see that shortly. So I'm not going to go through the solution, but there it is. Okay. Your rate of change is proportional to the value. And K is your proportionality constant. This doesn't confine just to population. Population, of course, can increase or decrease. You have a death rate in a population. And assuming your proportion of young to old and so forth doesn't change, if there's more death going on than there is birth, then you could have a decrease in population, so that K could be negative. Now, populations usually don't behave that way when you have a death rate. If your death rate starts exceeding your birth rate, there are usually things going on that make this model, excuse me, not quite applicable, although still gives you some indication. But radioactive decay is another. Okay, the rate of change of the activity of a radioactive substance is proportional to how much substance there is. You've got so many atoms, okay? And there's a probability in any given time interval that's a given atom is going to decay and produce radiation. And then that atom is no longer radioactive, at least that's the model. Often radioactive elements decay into other radioactive elements, and then things get more complicated. But you're going to get a different kind of radiation. So if you're measuring alpha particles, you're not going to pick up the radiation from beta particles. Although Geiger counter is going to pretty much pick up either. Okay, well, those complications aside, your assumption is that the more atoms you got, the more decays you're going to get in a given time interval. And that's pretty straightforward. So that your rate of change of the number of those atoms, or the decay rate within your sample, is going to be proportional to how much you've got. Well, those are two very common examples. And here we have, we can say that y prime equals ky applies to investments in certain cases, like bank accounts at constant interest rate. Radioactive decay, etc. I don't know why this board is so wobbly. I mean, I do, but let me see if I can do something. Uh-oh. I'm gonna lose my block. Covered it. Okay, that's a little better. And this is probably better still. Okay, there we go. Okay, so one of the simplest equations you can have, very easy to solve. Y is going to equal e to the ky. So I'll just tell you what the solution is. I said ky, it's kt, and then there's a constant out in front of it. And you can plug that in here. Y prime would then be ka e to the kt, and ky would be ka e to the kt. It's very easy to verify. And it doesn't matter whether k is positive or negative. If k is negative, e to the kt is going to be a decreasing exponential. If k is positive, it'll be an increasing exponential. Well, that's one example. Another example that looks a lot the same as the one we started with last time, y double prime equals negative ky, okay? And that's simple harmonic motion. And you get C1 cosine of omega t plus C2 sine of omega t, or A cosine of omega t plus phi, and you got to do little trigonometry to get from this to this, for omega is the square root of k over m. And that's one you should be familiar to from your physics background. If not, yeah, we're going to deal with it when we get to second order equations. It's as you see, you have a 2-parameter family of solutions. The 2 parameters could be C1 and C2, or they could be A and phi. And then if you're given initial conditions, as we looked at last time, you could evaluate C1 and C2. And you could equally, well, evaluate A and phi. Okay. From the solution of those equations, you get everything about simple harmonic motion. Okay, well, this and even this are pretty straightforward equations. And that's my double prime equals negative ky, Newton's second law. Okay, I've got stuff in my way here, but I think I'll get over here. Okay, mixtures. Mixture problems are a big deal, and they seem to give most people a fair amount of trouble. So we can think in terms of a tank. With some kind of fluid in it. And you got fluid flowing out of the tank, but you've also got fluid. Let's say you got a big old hose here, putting fluid into the tank. Okay, so you have fluid in, fluid out. Don't know how deep I want to go into this. We're going to say you got a proportion Rn of solute. Sorry. Trying to remember what letter your book uses. Got boards here trying to trip me up. So I want to revise what I've written here. Your proportion is not R1. R1's the rate at which it's coming in. Okay, hopefully you can read this. I can't tell if it's readable because my screen is backwards. It's a little weird, but you have fluid in here. The concentration is C sub N, and that's a concentration of solute. You can think salt water. Okay, so maybe you have a 0.03 concentration of solute. That would be 3% solute. Cn, concentration N would be then 0.03. Okay, and the rate in Rn, just think maybe 10 gallons a minute. Okay, so we maybe got 10 gallons a minute of 3% solution coming in here. Rn, 10 gallons, C in 0.03. And then you have fluid out. Concentration, C out, which is unknown at any given time until you solve the equation. Rate R out, rate R out. And let's assume that's known and constant, although might not be so. Maybe you're filling this thing in at 10 gallons per minute, and until the depth gets to a certain point, you're not going to have an outflow that's equal to the inflow. Now, that complicates things. That's a very interesting problem, but we're not going to deal with that right now. Might well consider it later. Okay, well, what we want to look at is in the tank, the volume of the fluid is V. And the amount of solute is Q, which is a function of T. Now the question is, at what rate is Q changing? Okay. Now you want to get your head around that idea. It's a pretty intuitive idea, but people tend to need to think about it a little bit. Okay, what's Q prime of T? Okay, well, Q prime of T is the rate at which the amount of solute is changing. And I wish I had that little board clean, but I don't. Okay, Q prime of T is the rate at which the amount of solute is changing. And okay, this is the rate of change of solute in the tank. And the bottom line is, and it's very obvious, if you think about it, it's the rate at which solute enters minus the rate at which solute leaves. Okay, now I'm going to need a little more board space here, so let's do this. Yeah, this will work. If I don't think I can get this over far enough, but let's redraw the thing and do a little briefer summary. So we have fluid coming in. R in concentration Cn. R out concentration C out. You have volume V solute amount Q of T. So Q prime of T rate of change of the solute in the tank is equal to rate in minus rate out. Okay, well, what's the rate in? You have Rn. Now, that's not the rate at which solute comes in. So let's put solute rate in minus solute rate out. Be clear that we're distinguishing the rate at which solute comes in from the rate at which solute goes out. And that's not Rn or R out, because Rn is the amount of fluid going in. Okay, how much solute is there going in? Well, the rate at which solute goes in, the amount of solute in a gallon of fluid, let's say, that goes in, is 3% of the rate of a gallon. Okay, so if Cn is 3%, you multiply 3% by the rate in, that tells you the rate at which solute is coming in. So that rate is Cn times Rn. Okay. Then it's going to be minus C out times R out. And it's very straightforward, except that we don't know what C out is. Remember, C out is unknown. Okay, but since C out equals the concentration in the tank, we conclude that C out is what? Concentration of the fluid is the amount of solute divided by the volume. So how much solute's in the tank? Q of T. What's the volume of the tank? V. And volume might be a function of T. Now, if the rate out is equal to the rate in, the volume's going to be constant. But if your rate out and your rate in are different, which might well be, then V will be a function of T, and we have to find out. Still, each step of this reasoning is fairly straightforward. So our conclusion is that Q of T equals Cn times rate in. Those are both known. okay, minus concentration out times rate out. Concentration out is Q of T over B of T. Times the rate out. And this is Q prime of T. This is a rate, again, rate of change of the amount of solute in the tank this is the rate at which solute enters this is concentration of the solute leaving, that's just this term, or this factor of this term, and this, which is the rate at which fluid leaves. And there's your equation. Now this equation tends to be pretty simple if your rate in equals your rate out. The rate of fluid going in equals the rate of fluid going out. In other words, if you have a constant volume here and you're pumping solute, pumping solvent in and pumping the contents out at equal rates. Okay, that's a fairly simple equation. It gets less simple if your volume is changing. Depending on how your volume is changing, if your volume's changing at a constant rate, then that's okay. That's not too hard to deal with. If your volume is changing at a quadratic rate, which would be the case if you're allowing the contents to flow out due to the pressure in the tank, and you have a cylindrical tank, then you have a quadratic volume function. Gets a little more complicated. If you've got a conical tank, which is fairly common, it's even more complicated because it's then V is no longer a quadratic function, and things get out of hand pretty easily. Okay, in the simplest case, where R in equals R out and volume is constant, we get a simple linear equation, which we'll learn to solve next week or the week after, and it's easy to solve. Okay. Well, that's an important application. It's important because a lot of things mix. For chemical engineer course, you do a lot of mixing. But in other fields, civil engineering, and then the whole concept of things entering and leaving a system, even systems engineering, you find it a lot. Okay, well, that's kind of a big deal example because that one is, as I say, one tends to give people trouble. Okay, now something that's relevant to things that are very serious things that are going on right now is spread of disease. Now, the disease could well be COVID. SPRED, let's put an A in there. Okay, spread of disease. Let's say that I go into a big box store or supermarket and there are 100 people in there. Okay. One person is spreading the disease. And incidentally, this applies to rumors. It applies to all kinds of things. There's sociological aspects to rumors. Of course, there's sociological aspects to disease. We're not going to get into those. Those complicate our models. But our basic model gives us kind of a baseline for understanding what happens with the disease. And no amount of conspiracy theory or disinformation or lies can change the model. Now, that doesn't mean that there aren't things that mitigate the validity of the model, but the model itself is a perfectly objective thing, and then you can debate how you deal with it. You can debate how things change the model. That's a valid debate and a useful, necessary. Okay, anyhow, you got spread of disease. You got one person in 100 spreading this disease. And now everyone suddenly becomes confined. Maybe there's a civil emergency. Maybe there's a cyber attack that locks the doors. Nobody can unlock them. Of course, people will figure out how to get out. You break doors. But just hypothetically, everybody's confined. In that situation, you can at least visualize, and it's not a pleasant one to visualize, but hopefully the bathrooms still work. Okay, everyone is confined, and hopefully there's enough food on the shelves if it's a supermarket or something, that it's not a terrible disaster, just a pretty big inconvenience. And maybe the inconvenience is less than the inconvenience of whatever's going on outside. You don't know. But anyhow, everyone's confined. So what's going to happen now? Well, this one person is going to inevitably, if it's a highly contagious disease, which is what we've got going on right now, that one person's going to spread it. Now, it's going to take a few days for the next person to get infected and to start spreading. But we're going to assume that once a person is infected, they're instantaneously going to start spreading. That's unrealistic. And of course, that's one way the model has to change a little bit. It just gets mathematically more complicated. It doesn't really change the overall trend of the disease. It just changes your constant, the constant K that we're going to use here. Okay. Let's say it doesn't significantly spread the overall behavior of the spreading. Okay, so everyone is confined, and we assume that infection is immediate. Keep leave the A out of spread. And I know perfectly well how to spell spread, S-P-R-E-D-D. Just in writing the E, the A starts a lot like the D does, and my hand does the wrong thing. Okay, and that's my excuse. I just don't know how to spell. Okay, infection immediate is the ability to spread. Now, what transpires? Okay, well, We start with one infected. And 99 uninfected. And I just realized that I'm writing really low, so nobody can read it, but there it is. Okay, infection is immediate, as is the ability to spread. And we start with one person infected and 99 uninfected. Okay, get this board over here a little bit so we can see everything. So I'm worried about that. It's okay. Okay, what happens next? Uh-oh, I don't have another one of these. I was assuming I would. Okay, let me rearrange boards here a little bit. Get this one out. Shoulders locked in. I can't handle this at that height with my right hand. Hopefully I don't knock anything over and break it. Okay, so I'm going to move from here to here. Don't really have room to stand over there. I'm going to change this. I've got a new setup here. I didn't anticipate. Okay, we're good there. Okay, so I'm going to just write up here and bring this over a bit. Okay, what's going to happen now? After some time, somebody's going to get infected. So you're going to have one person infected. Now you're going to have a second person infected. Okay. That doubles your probability, if you're not among the infected, of getting infected. So eventually, someone new gets infected, and I'm writing too high. Okay, we can probably handle that. Eventually, someone new gets infected. So now you would say you expect the probability of the next infection to be doubled because now you got two people spreading. Okay, well, that's almost true. Now, your probability of infection doubles. And so does the probability of infection of everybody else who hasn't been infected. But see, now there are only 98 people left to infect. So we're going to say since there are only 98 uninfected people left. Okay, so how are we going to deal with that idea? And then you got a third person infected. Now there are only 97 left. So if you're still uninfected, your probability is now triple what it was. But the probability in the whole group is not quite triple because now you've only got 97 people that could be infected. Okay, well, we deal with that without spending too much time on it. And you want to think this through, make sure you understand it. I'm going to say at every step, the probability of the next infection is proportional to the number infected times the number susceptible. Okay. Now I say the probability of the next infection, but that's not quite right because over what time period do we consider that probability? So I'm going to say this isn't quite right. Probability of the next infection. I'm going to say the rate of new infections. I don't know where that N came from, somewhere in my fertile brain. Okay, the rate of new infections is going to be proportional to the number infected times the number susceptible. Now the rate kind of feels like the probability of the next infection, but I did say over the next hour, the next infection. What's the probability of the next infection over the next hour? That becomes a rate of infection. Think about that a little bit. So we can say I'm just looking for a letter for the number of infections. If N of T is a number, that's the obvious letter to use, is a number it's a number of infections at time T. Then the derivative of that is a rate of infection. So N prime of T is equal to some proportionality constant times the number infected times the number susceptible. Well, what's the number infected? That's N of T, isn't it? Okay. What's the number susceptible? Well, in our example, that's 100 minus the number infected. That's your 98 or 99, then your 98, then your 97. Where your number infected is your 1, then your 2, then your 3. These two have to add up to all your people, assuming everybody's either infected or susceptible. Now we're kind of assuming that once infected, you stay infected forever, at least until this model is abandoned because it no longer applies. And that's not realistic, but you can easily expand this a little bit by including another number, which is the number who are immune, okay? And you would subtract that from the number who aren't infected and add the number who aren't infected with the number to the number who have not yet been infected, and that still gives you your number susceptible. So that can be dealt with. Okay, so that's not important. We're not going to worry about that right now. It's a fairly obvious idea. Okay, well, your number infected is N of T. Your number susceptible is 100 minus N of T. So N prime of T equals some proportionality constant, and that proportionality constant just depends on how quickly the disease spreads. Depends on its infectiousness. It could depend on the average number of people who are infected by a given infected person. All kinds of ways to get a handle on K. But anyhow, that's K times your number infected, which is N of T, times the number susceptible, which is 100 minus N of T. And if you got number recovered, well, that complicates things a little bit. This wouldn't actually be number infected. This would be number transmitting. And you'd subtract the number recovered from the number infected. And then you'd add the number recovered to the number who haven't been infected. That's your number susceptible. Okay, well, that's just a fine point. Once we understand the model, it's pretty easy to understand how we would incorporate those slight modifications and even other modifications, which might be depending on behavior. As soon as somebody starts coughing or sneezing, you make them go over into that corner, hopefully isolate them in some room, and throw them a little food every once in a while. Well, you take care of them as best you can. And worry about that part of the model. That's where a lot of decisions have to be made. But they're made within context of understanding how diseases spread rather than whatever side of the political spectrum you have to be on. Okay, decisions could be made within this context. Different people will have different opinions on how that should be dealt with. That's valid. Rejecting the model, not such a good idea. That's where you start. Okay, well, anyhow, you have this. Here's your differential equation. Okay, that's all there is to it. And then we figure out how to solve the equation. This, again, not a particularly difficult equation to solve. It's what we call separable. So it just comes down to a couple simple integrations, and make sure you keep your integration constants there, because that gives you a parameter in your family of solutions. Okay, well, cooling, draining a tank, it's one of my favorite models, since I often use it as an example in both mathematics and physics classes. So we'll probably talk about it. We've got 20 minutes here. Okay. Cooling. Okay, I think your book uses a cup of coffee. I like to use a turkey you take from the oven because I like turkeys. Not too many, just a couple a year, but otherwise you get tired of turkey. It loses its thrill. You don't really get tired of it. It's always good. Okay, and you can model that. How thrilling is it to take your first bite of turkey when it's been so much months after you've had your last bite of turkey? And then on that number of months before, how much turkey did you have and what time before that? It becomes a very interesting model. I got to do that one. I had never thought of that one before. Okay, but now we're going to do cooling. Okay, so your turkey cools at a rate proportional to how far its temperature is above room temperature. Okay, well, if T sub room is the temperature of your room, and T not letters, turkey, then if you understand, the first model we did, y prime equals ky, should be pretty easy to understand why t prime of t equals k times t minus t room. Now your book uses a different subscript on the temperature of your surroundings. I don't remember what it is, but I always use T room, so I'm going to use T room. Very clear what it means. And from that, you'll understand the notation of the text much better. So that's it. This says the rate at which this thing changes is proportional to, by the proportionality constant K, how far the temperature is from the temperature of the room. Now, if your room happens to be the oven and the temperature of your turkey is less than the temperature of your oven, the model still applies. Doesn't apply just to something cooling, it could apply to something being heated. So it applies to cooking your turkey, where your room temperature is the temperature of the oven, and it applies to what then happens when you take your turkey out and allow it to cool for 20 minutes. So you can cut it without trouble. Okay, so straightforward model, very straightforward model. Now things mitigate that model again. Your oven is going to turn on and off and on and off. The coils are going to heat up and cool off, assuming you have a oven that heats by coils with the turkey exposed to the coils. Okay.
I have a question.
Oh yeah, Richard, go ahead.
So the way you have it written out right now, I would think either K would have to be a negative number or T room and T would have to switch, because the way it's written now, if K is positive, then
K can certainly be a negative number.
Okay.
Okay. Just like in the first example, I think I said, not you check me because I might not have. If you have radioactive decay, K is going to be a negative number, and your e to the KT is going to be decreasing exponential. Okay. And you got to get the same thing here. You just get a slightly more complicated expression, and it's very simple to understand. So when we actually solve this equation, it's just a matter of integrating reciprocal of T minus T room, which is going to give you a natural log of T minus T room equals KT. T being little t, your time, not your temperature. And then you change that to exponential notation, just using very straightforward pre-calculus. Okay, so it's a very, 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 very simple equation to solve. This one would be a bit less simple, but it comes down to the same thing. Just you're going to have to maybe use partial fractions to deal with the fact that your expression here is quadratic in n of t. And you're going to have to integrate that, the reciprocal of that, in a way that we're going to see actually very soon, maybe even certainly next week. It's what we call a separable equation, and very easy to solve. Okay, and very intuitive, the solution. Okay, well, that's this model. Now I've got to find a little more board space. I think I've got another board there that's blank on the back, but we'll see. If not, I might have to. Well, I've got one. I've got a board that I don't like to use because it's kind of scuffed up, but we'll use it if we need to. Okay, so your question was a good question. And K can certainly be negative. And it would be negative if you're cooling the turkey. It'll be positive if you're cooking it. Okay. Yeah, I love this one. And I don't remember, I mean, you had my physics course. I don't remember if we did this one. Although there's a good chance that we did. Okay, that one is clear. This one has been written on. And this one, I think, we'll see. Back of this one. I can't even tell if that's board or just plain wood. Looks like it has possibilities. I'm going to flip this one just because it's a better board. Assuming, yeah, actually it's not that great. Actually, it's pretty bad. We're going to use it anyway. And that's the mark I just made on it to see if it was any good. Certainly looks like I could have cleaned this one better. Okay. So, next example, we deal with fairly quickly. And I might even quickly do the solution. You got water in a cylindrical tank. You got the water level. You got water flowing out of clean hole. Water's flowing out. So obviously, as the water level decreases, the pressure decreases, the rate at which water flows out decreases. Okay, turns out from Bernoulli's equation, from conservation of energy, from any way you, Bernoulli's equation is just a statement of conservation of energy, that the rate at which the water level changes, we'll call the water level Y. turns out that dy dt is k times the square root of y. Okay. And that goes, since you know the physics, the rate at which water flows out of here is going to be proportional to the square root of the pressure, and the pressure is proportional to how far you are above the hole. And actually, we're going to say that clean hole is at level y sub f. When I wrote this, I was assuming you're measuring the water level from the position of the hole, in which case yf would be 0, and you'd have k square root of y. It's going to be k square root of y minus yf, and that doesn't complicate the problem at all. Okay. Well, I'm going to solve this one, okay, because you're going to see severable equations very soon anyway, and it's really simple. Okay. I can algebraically rearrange this. Now, I'm not actually doing the algebraic rearrangement. I'm making a statement about derivatives and differentials and so forth, but it acts just like an algebraic operation. So I can say that if this is so, then we can do this. Okay, and we can do this anytime we have continuous functions and so forth, and everything here fits the bill. Okay, so we just rearrange the equation as if it was algebra. Then we integrate both sides of the equation. Remembering that k is a negative constant. And I'm actually going to write this with a negative on k, so k can be a positive constant. Okay. Well, antiderivative of square root of y minus yf, very simple. You do a u substitution, let u equal y minus yf, then du equals dy, and you have du over square root of u, and that gives you just the square root of y minus yf, except, check that, if you take the derivative of the square root of y minus yf, you get 1 over 2 times the square root of y minus yf. So it had better be 2 times this, so the derivative matches this function. And this is negative kt. And there's your solution. You got your function y right here. Now, if you want to get the function of y explicitly, you square both sides. And before you square both sides, you probably ought to go ahead and divide by 2 so that you get y minus yf equals the square of this quantity, negative 1/2 kt. And then you get this, which is a quadratic function of t. You do have an integration constant here, which I carelessly left off. Now you have a 1 parameter family of solutions, and this is way down below what you can see. So maybe I better, let's see, I've got this. And you can probably see this even if you have the watermark. So I'm going to rewrite this. So you get y minus yf equals negative 1/2 kt plus your integration constant squared. So that y equals 1/4 kt squared minus c kt plus c squared plus yf.
I think it's 1/4 k squared t squared, right?
Yep. Yep, I'll do that down here where I that. So and I had the k squared here. I didn't have it here. That's k. Yeah, okay. Okay, there it is. Anyhow, okay. Now, one reason I wanted to do this example, and I think I've got a mistake there. Something's not working out. We should really have. Oh, never mind, it works out. Okay. The reason I wanted to do this, one reason is because if this is the source of water flowing into that tank that we did with the mixture problem, and I kind of alluded to that, or if this is the tank and water is flowing out without being pumped just by gravity, then you have a very interesting mixture problem. Okay, this is very straightforward. But the mixture problem that comes out of this, the type of mixture problems that come out of this, be pretty interesting. Now, there's one more thing I wanted to do. We have got 5 minutes. And of course, I know that you understand circuits, or at least you've seen circuits. Okay. So I'm not going to have time to do too much with this. I'm just going to kind of remind you, also if somebody happens to be seeing this video, we want to accommodate them also. Okay, so let's just say we've got a network of sources, capacitors, inductors, resistors. Now by itself, this is just an RLC circuit. So if we've got a switch in here somewhere and close the switch, the capacitor is going to tend to charge, and the charge on the capacitor will then tend to oppose the increase in the charge. The inductor is going to charge up. But the inductor is going to develop a current, which creates a back EMF by induction, and the resistor is going to tend to resist the change in current. And I can't go through too much of that, but there are rules for these things. And then if we have more circuit elements, like say we've got a capacitor here, and an inductor here. I don't do inductors backwards very well, do I? Anyway, that's an inductor. And and maybe even something else here. Say another capacitor here. And maybe instead of a constant source, you have some kind of a alternating source. Then ask yourself how the circuit behaves. Okay, well, we have rules. Okay, you're going to get currents. You're going to have a current here, call that I1, a current here, call this current I2, a current here, call this current I3, and a current here, which we can call I4. Now these currents go around loops. So let's designate loops here and designate the positive direction for the loop. Well, all these currents happen to be in the positive direction that I've chosen for each loop. That'd be the clockwise direction, although we usually use counterclockwise as the positive direction. We're not analyzing the fields here, so no reason not to use this direction, but conventionally you'd probably be better off drawing your loops counterclockwise. Okay, so we've got these loops. We have the same current. Well, okay, we've got a current I1, I2, I3, and I4. Now I1 here, some of I1 goes to I2, and some of it goes here. Or maybe I2 is actually negative, so even though we said it's positive, it turns out to be negative. We're going to get a negative sign when we solve our equations and stuff. And we don't know what direction any of these things go in. And it really depends on the direction of your source and what else is happening in the current. It's very complicated. But we have rules that say that we have some current here, which I'll call I4. And I1 equals I2 plus I4. Or if you add I1 and then subtract I2 and I4, you get 0. Okay. In other words, the net current into this point here, there's no way current charge can be stored. Net current into this point has to be 0. So you have this. You also have voltages. I'm actually not going to be able to do this today, but for the ability to remind you, all these currents are functions of time. Whether this is a constant source and you close the switch, or this is an alternating source where things are changing all the time. Your current, when your current changes through an inductor, that's what gives you a back EMF. The current through a capacitor is the rate at which charge is changing in that capacitor. And the charge on the capacitor gives you a voltage on the capacitor, an EMF, okay? So the sum of all your EMFs around any loop has to be 0, okay? So the sum of your EMFs is 0 through any loop. The EMF of an inductor is Li prime, where I is the current in the loop. So for example, for this inductor, it would be L for this inductor times I4 prime. And it'd be negative. EMF of the capacitor is CQ, where Q is the charge of the capacitor. I'm not going to worry about the signs. I'm just going to write these. This is a plus or minus. This is a plus or minus, and we'll talk about why. We'll talk a little bit more about these things. We'll do a little of that next time, or I'll do a little bit more in the video because I'm not going to be here for class next time. There's your EMF of the capacitor. You sum all the EMFs around any loop and you get equations. And these are differential equations because you got an I prime here, you got a Q here. And also, the current is Q prime. So you end up with second order equations. You do everything in terms of Q. So I prime will be Q double prime. And you get these equations for these loops, and you get a whole system of equations. And it's quite interesting and quite powerful. Almost everything depends on circuits in some way or another. Okay. Well, that's going to be it for today because I've got another class coming up. But I think I've got them on a 15-minute delay today. So, look interesting?
Thank you.
Okay. See you next time. Take care, Richard.
All right. You too.